Let's consider the problem D. Suspicious logarithms. Let f of x be the floor of the binary logarithm of x, and let g of x be the floor of the logarithm of x with base f of x. We are given q queries. We need to find the number of numbers from L to R. Not the number of numbers, but the sum of g of k across all these numbers. Modular 10 to the 9th plus 7. This is kind of pretty standard problem. So, idea in this problem is, rather than considering all i's from L to R, yeah, so what do we need to do? We need to sum g of k for k from L to R. Actually, you can start with g of k. So let's sum over all possible g's. Let me call it capital G. Then you need to multiply g by the number of such k that g of k equals g from L to R. So this is the main idea. For each number g, we will count the number of such k's for which this is the answer. This will be a lot faster, simply because logarithms cannot be big. Yeah? Even binary logarithm is at most 60 for such numbers. And if you consider logarithm with bigger base, it's even less. So you cannot have logarithm greater than 60. So I can write like from g equals 0 to 59. So the only hard thing is to find this sum. For that, I will be even more strict. I will consider, instead of, let's do it, number of k's from L to R such that g of k equals g. How to calculate it? Instead, we will find for all L to R sum of for f from 2 to 59 such case that f of k equals f and g of k equals g. Yeah? Why is that? Because what does it mean? It means that I want k to be with this value of g. And what about f? Actually, I don't care what the number of f is. Yeah? I allow f of k be either 2, either 3, either 4, or 5, or 6, or 7, or 8, or 9, etc., or 59. I know that f of k is in this set. F of k is definitely in this set. So I just say, choose me one number f of this set, and I only want such case for which number f is this particular number. Then I sum over all these f's, and I will end up with this, yeah? It's like, what if I sum up all the red balls, all the green balls, all the blue balls, the yellow balls, the white balls, etc.? I will just get the total number of balls, yeah? Because if I add balls with every color on Earth, then I simply don't care about the color. Any color will satisfy me. This means that I just will get a total number of balls of any color. But still, I do this because if I fix the color of ball, or I fix the value of f, it will be easier to calculate. So let's do it. Now we are interested in the following. So we know some f fixed and some g also fixed. We want to find the number of such number k's from L to R such that f of k equals f and g of k equals g. How to do that? Actually, for logarithms, it's kind of easy. Yeah, what can you say about a number I if it is its logarithm base b is like t? It is definitely at least b to the t, because if it is less, then the logarithm would be at most t minus 1. But it is also less than b to t plus 1. So this is what we know. Actually, we know that I is in some segment from bt to bt plus 1. Yeah? So let's rewrite it. Let's rewrite it. Sorry. Again, sorry. So we know that f of k is f and g of k is g. And let's also add that k is from L to R. Let's rewrite. So we know that logarithm of k base 2 equals f. What about the second part? It says that logarithm base f of k floor equals g. But we know that f of k is f, capital F. So we can replace here with capital F. And finally, we know that k is between L and R. And as I said, the two top conditions can be also rewritten. The first thing says that k is from 2 to f to 2 to f plus 1 minus 1. Second says that k is from f to g plus 1 minus 1. And the final one says that k is from L to R. And this can be rewritten as simply k is from L to R, where L equals maximum of 3 left borders, and R is the minimum of the 3 borders. Okay. So how to calculate such number of k's? It is easy. You just need to take minimum, no, I think maximum of 0 and R minus L plus 1. This is the formula. And this is R and L. There is one nuance. Nuance is that this number can be out of int64 easily. Yeah. We, for example, can consider 59 to the power 60. It's way too big for int64. This is why you kind of need to be cautious while calculating powers. Yeah, for example, you do not need actually this power here. You need minimum of this or of the and this. Actually, you need to calculate minimum of 2 to f plus 1, f g plus 1, r plus 1 minus 1. I will then traverse to this. You will need minimum of 2 to f plus 1 and r plus 1, and minimum of f of g plus 1 and r plus 1 minus 1. So instead of a power, you need the minimum of a power and some int64. How to do this? To do this, you can make just some simple formula like let's write a function long power. A, B, and some border. Let's write what it does. It calculates minimum of A to power B and B. What does it do? So first of all, I will write incorrect approach. For int I equals 0, I less than B plus plus I, ans times equals A, and return minimum of A ans and B. This is incorrect because, as I said, this can overflow. Yeah. What about some fix? We will intercept this overflow sooner. So we will say here that if answer is greater or equal B, then return B. Otherwise, we just return ans. This is also incorrect. Yeah, for example, why is it incorrect? Because if this is your border, and this is border of int64. So this is int64, this is your border, and this is current answer. It can happen that you multiply your answer by A, it is greater than border now, but it is also greater than int64. So overflow happens, it is now some random number, and you simply don't know what is happening here now. Maybe it will be negative. This is also a bad option. You somehow need to understand that ans will be greater than B without calculating it. And there is a way. There is a way. How to check that ans times A is at least B? You just don't need it. Actually, you need to check whether ans is let me think. So it is equivalent to ans being at least. Okay, let me write it like this. Ans times A is at most B. Ans times A is at most B. If and only if ans is at most B over A floor. Okay, assuming that it is greater than 0, this is greater than 0, and this is greater than 0, and nothing overflew. Yeah? So instead of this condition, which we cannot check because this can overflow, we can check this condition. So the final function will look like this. So ans equals 1, then we iterate. Yeah, and we check. Does it make sense to multiply ans by A? So if ans is at most B over A, then ans times equal A. Otherwise, ans just sets to B, and in the end it will also be B. And in the end we return ans. So this is the nuance that I was talking about. I explained it.